Hello everyone, in this video we're going to be learning how Le Chatelier's principle explain the shift in the equilibrium anytime there isn't a disturbance. So once you have achieved an equilibrium reaction, you can disturb that equilibrium by either changing the concentrations of reactants or products, or you can change the volume, pressure, or even temperature, and their equilibrium will shift so that it will minimize the overall change. And I'm going to take an example here to explain this Le Chatelier principle better, because that's just how it works. I have this equilibrium reaction where we got silicon dioxide solid reacting with the hydrogen fluoride gas, making silicon tetrafluoride and then making water along with it. So before I do anything, I want to go ahead and write a Kc expression for this particular equilibrium reaction. So I'm going to have the concentrations of the product, so it's going to be SiF4 times the concentration of water to the power 2. Divide that by the concentration of HF to the power 4. And remember, we didn't really include the SiO2 because it's a solid. In a heterogeneous equilibrium, if you have the solids and the liquids, you don't really include those in your equilibrium constant expression because their value or their amount is going to be so high that it's not going to affect the expression. It's not going to affect the Kc values either. In addition to that, another important point you want to notice here is the value of delta H is positive, which means it's going to be a endothermic reaction. It's important to know whether you're dealing with an exothermic or endothermic reaction in order to figure out the effect of temperature on the equilibrium. So let's just focus on what's going on. So first I'm going to be looking at the effect of concentration. In the effective concentration, let's say I'm adding HF. So if I'm adding HF, you're going to have a lot of reactants, and when you have a lot of reactants, then what you need to have, then in that case your reaction will shift to the right in order to lose some of that reactant and in order to make some of that products so that you can reestablish, so that you can get back to that Kc value that you actually needed. So whenever you're adding the reactants, it usually shifts to the right side. So in this case, your equilibrium will shift to the right. What about the second case, removing gaseous water? So now you got to look at what's happening to the water, and we have the water on the reactant, on the product side rather. So water being removed, there another way of saying it, decreasing the concentration of gaseous water or the vapors here. And when you're losing water, what's going to happen? You now have less product than you're supposed to have. So in order to recover those lost product, what you have to do, you would have to shift this equilibrium to the right so that you can make those lost products and go back to the Kc value. So in this case, when you're losing some of this water, your equilibrium will still shift to the right to recover any lost water vapors there. What's going to happen when you're adding SiO2? Well, SiO2 is actually a solid. So solid is not a part of equilibrium constant expression. So as a result, anytime you're adding or removing solids or even liquids in a heterogeneous equilibrium, they're not going to have any effect on them. The only time they would have effect on them if you completely remove them, which is unlikely to happen. So a lot of time when you're changing these concentrations, you're kind of changing it some at a time. You're not going to be like taking it out all the way. So that's how going to be the effect of concentration. Let's look at what's going to be happening to the effect of temperature. Now, whenever you increase the temperature, so I'm going to write that down here. So temperature goes up, it favors endothermic reaction. And whenever your temperature decreases, that favors exothermic reaction. So that's something you want to make sure you memorize. So when I'm looking at this, my particular reaction here, the way it's written going forward, we have a delta H of positive. So what does that mean? That means we have a endothermic reaction going forward, but then at the same time, it also means when you're going backward, it's going to be a exothermic reaction. So when we adding heat, what we're really doing, we are actually increasing the temperature. So if you're increasing the temperature, it's going to favor the endothermic reaction. And which way it's going endothermic? So if I go back, we got this going to the right side is going to be the endothermic. So as a result, this is going to shift to the right side. So that's how you're going to be determining the effect of temperature. You can also say, just decreasing temperature, or you can even say lowering the heat. So in the next example I have here, it's saying decreasing temperature. So remember, whenever your temperature drops, you are going to be favoring the exothermic reaction, and the exothermic reaction for this particular case is going to be going backward. So this is going to be shifting to the left side. What about the effect of pressure and the volume? There's a couple of ways you can kind of think of, but before you do anything, make sure you know the relation between the pressure and the volume. If you recall Boyle's law says the pressure and volume, they are inversely related with one another. Another way of saying, if pressure goes up, your volume goes down. Or if your pressure goes down, your volume goes up. So you can memorize using one of those parameters, like maybe focus on the volume and then always be able to relate if they're asking the question in terms of the pressure. So if you have, think of this, if you have a large volume means you can accommodate more moles, or to be better, more gas moles. As the name is kind of makes sense, because if you have a bigger container, you should be able to accommodate more gas moles in there. But if you have a small volume, then you will not be accommodate more gas moles, but rather you're going to be accommodate less gas moles. And that's exactly what we're going to have to look into when we looking at the effect of volume and the pressure. So in the first one, I'm saying we are looking at pressure increases. So when your pressure is increased, what's happening to the volume? Well, clearly your volume is going to drop. So as a result, you're going to be favoring to the formation of less gas moles. Okay, now you got to go back and see which side has less gas moles. So if I go up there, and I can clearly see I got 4 gas moles, 4 HF on the reactant side, and on the product side I got 2 gas moles coming from the water and 1 gas moles coming from the SiF4. So the right side still have less number of gas moles total than what you have on the left side. So since we are decreasing the volume and increasing the pressure, we should be shifting to the side that has less gas moles, and we just figured out that your less gas moles are going to be on the right side. So this particular one is going to be shifted to the right side. And what if the volume increases? Volume increases, another way of saying your pressure is going to decrease. So pressure drops down, your volume increases. Now you want to have your equilibrium shifted to the side that has more gas moles in there. And obviously, when we go back, which side has more gas moles? We got 3 gas moles again on the product side and 4 gas moles on the reactant side. So it should shift to the left side now. Okay, what's going to be the effect of catalyst? Catalysts usually don't have any effect on the equilibrium. We know catalyst does lower the activation energy, but it lowers the activation energy for both sides. It's going to lower the activation energy for the forward reaction, and it's going to lower the activation energy for the reverse reaction as well. And as a result, there is no net change in the concentration, so there is really not going to be any effect whenever you're adding a catalyst. That's how you're going to be looking at the Le-Chatelier principle, but before we go out, we want to make sure you guys can do this problem here. To be a better idea, you can pause the session and figure out what's going on with these disturbances here. and let's see if they matches with what I got here. Hopefully you guys paused the session and figured out what's going on with these changes in terms of the equilibrium shift. Before I do anything, I do want to kind of go ahead and write down the equilibrium constant expression. So Kc is going to be the concentration of CO times the concentration of H2, divide that by the concentration of water. And remember, I'm not going to be including the carbon because that's a solid. In addition to that, we are adding the heat on this reactant side. So that's another way of writing what type of reaction. So when you're adding the heat on the reactant side, that means your delta H is going to be a positive, or that's another way of writing an endothermic reaction. If you have heat added on the product side, then it would have been an exothermic reaction, or if you have the delta H to be negative, that would have been an exothermic reaction. So you want to make sure you know different ways of writing the exothermic and endothermic reactions. So when we add in carbon, what's going to happen to this equilibrium? Well, remember, carbon is a solid. So since it's a solid, it's not going to be affecting any of these Kc values because it's not a part of equilibrium constant expression. So as a result, there is gonna be no effect when you either remove carbon or even add carbon. As long as you don't take it away, all of it, it shouldn't matter in terms of the equilibrium. Increasing pressure. So when your pressure goes up, what happens to the volume? Your volume comes down. And when your volume comes down, you're going to be going to the side that has less gas moles. And now we got to figure out which side has less gas moles. Well, we got a total of 2 gas moles on the product side, and we have a total of 1 gas mole on the reactant side. So since we're increasing the pressure, we're going to be going to the less gas moles, or another way of saying, in this case, we're going to be going to the left side. And if you want to memorize this um, acronym here, so IPL means increased pressure goes to the side that has less gas moles. But either way, if you understand in terms of the volume better, that's fine. That's how you want to keep it. If you want to have an extra side note that just confirms your answer, then you can use this IPL acronym as well. Okay, what's happening when you're removing water vapors? Well, if you're removing the water vapors, that's another way of saying decreasing the concentration of water. So when the concentration of water is decreased, you have less reactant than you should have. So since you have less reactant, you must have some of your products going back to recover those lost reactants. So as a result, it's going to shift to the left side. What about removing CO, carbon monoxide? If you remove carbon monoxide, and removing carbon monoxide will decrease the amount of or the concentration of CO that you actually need, and to recover that concentration, your reaction must shift to the right side. Okay, increasing concentration of H2. Now you have more H2 than you need at the equilibrium, and in that case you must lose some of the H2, and in doing so you must be making some of the H2O gas so that you can recover that Kc value. So in this case it's going to shift to the left side. What about removing heat? Well, remember, this is an endothermic reaction going forward, and removing heat, if you recall, it's always going to favor exothermic reaction. And since it's going to favor exothermic reaction, it must shift to the left side because your reverse reaction is indeed going to be your exothermic reaction, as your forward reaction here is going to be the endothermic reaction. All right, so this is how you're going to be looking at different effects when you looking at your equilibrium shift according to the Lee-Chatelain principles. If you have any questions, feel free to leave any comments in the section below.